Hello everyone and welcome again to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last lecture, we started our foray into the various loss functions that are used while training machine learning models. And we started with the simplest ones, the mean squared error and the mean absolute error. Today, we'll continue this journey forward. First, we will take the example of the mean squared error and solve a couple of analytical problems involving only one feature to get a feel for how these optimization of parameters will eventually work, and then we will proceed on to other types of loss functions which are used in various machine learning models, including the logistic loss function as well as the cross entropy loss functions and various types of other loss functions, including the mean absolute percentage error and so on and so forth. So let's go ahead and get started. So the topic that we are at now is loss functions in ML models, and in the last lecture we already started with two of them. They were the mean squared error or the L2 loss and the mean absolute error, which is the L1 loss, and we wrote down the expressions for these. So L MSE was equal to 1 over n sum I going from 1 to n yi hat, the predicted value, minus yi whole squared, and the mean absolute error on the other hand was equal to 1 over n, the number of data points, sum I going from 1 to n, the absolute value of yi hat minus yi. Right. So these were the two expressions we looked at. We looked at the pros and cons of these, and you know the notation, right? Number of data points, this is the predicted value and this is the true value. We also saw how the mean squared error has a firm theoretical footing in statistics, right? So this is derived from the maximum likelihood estimation of the parameters assuming Gaussian noise, right? And this concept of the maximum likelihood estimation will come back in some of the other loss functions also that we will discuss going forward. Now, as I had mentioned, I want to start today by introducing a couple of analytically solvable problems. So this is going to be an example of linear regression in one variable solved analytically using the L2 loss, right, or the mean squared error loss. So let's take a very simple case here. Let's take the model to be y hat equals beta naught times x, right. So here we are just trying to fit a straight line and there is only one parameter beta naught and there is no intercept. So we are assuming that this particular line, right, that passes through the origin 0 0. So if this is the case, how do we proceed forward, right? So to find the optimal parameter, we will have to write down the loss function, and here, like I mentioned, we are going to employ the L2 loss function. So let's go ahead and write down the expression for the L2 loss function. So the L2 loss function is one over n sum I going from 1 to n and the difference between the actual and the predicted value whole squared. So yi minus beta naught xi whole squared, right. So this is the true value and this is the predicted value. Okay. So this is the mean squared error and we want to go ahead from here. Now to find the optimal parameter beta naught, you know that we have to minimize the loss function. So you have to do del L2 by del beta naught, you have to evaluate that and set it to 0, right. So let us try and do that. So first we will compute del L2 del beta naught, right. So this is equal to del beta naught of 1 over n sum I going from 1 to n yi minus beta naught xi whole square, right. So if you want to calculate this, 1 over n is a constant, so it will come out of the derivative and the summation can also be taken out of the derivative. So that comes out as well and you are left with del beta naught of yi minus beta naught xi whole square. So at this point you can apply the chain rule for the evaluation of this derivative, which will become twice of yi minus beta naught xi. So I am first evaluating the derivative of this whole function times the derivative of whatever is inside the parenthesis versus b naught, so beta naught. So the derivative of yi minus beta naught xi versus beta naught, right. So this is what we have and we can now simplify this, right, to 1 over n sum I going from 1 to n twice of yi minus beta naught xi times the derivative of this expression versus beta naught is just minus xi, right. So this is the expression that we obtain. So now we can go ahead and simplify this expression. So del L2 del beta naught should be equal to 0 and this means that 1 over n sum I going from 1 to n 2 times and there is a minus here, so I will write the minus here, 2 times xi yi minus beta naught xi squared and this whole summation should be equal to 0. Now these terms 1 over n and minus 2, they are all constants, right. So they can be brought to the other side and they will disappear and essentially what we have is sum I going from 1 to n xi yi minus beta naught xi squared equals 0. So this can be split into 2 summations, so that is I going from 1 to n xi yi minus beta naught comes out of the summation because it is a constant and what we are left with is summation I going from 1 to n xi squared equal to 0. So now we can write the final expression for beta naught, which is simply sum I going from 1 to n xi yi divided by sum I going from 1 to n xi squared. So this is the equation for the best fit parameter. Okay. So that is really nice, but we can ask the question, right, would we get the same sort of expression if we followed the linear algebra derivation that we had done some lectures ago, and will we get the same answer, right. So the expression that we had derived, right, using matrix and vectors was beta hat equals x transpose x inverse x transpose y, right. So this was the expression that we had derived, and a good question to ask is that will these two equations, will they match each other or not? So ideally they should. Let's check whether this happens or not. So what is now X transpose X, right? If you remember, X is the matrix of the features. So X is a matrix of features and Y is the vector of true values. So in our case, right, there is only one feature. So the matrix of features is actually a vector of features, right. So there is one feature for every data point, right. So X transpose X therefore simply becomes the dot product, right, of the two X vectors. So this becomes sum I going from 1 to n xi squared and inverse of that, right. So this is the first term, X transpose X inverse, and again this also is very simple because this just now means X transpose Y. So X transpose is x1 x2 up to xn, let us say there are n data points, and the Y vector is y1 y2 y3 up to yn, right. And clearly if you multiply these two vectors, right, you will just get their dot product, right. So this means that the second term here is sum I going from 1 to n xi yi. And finally we can, because this is inverse is now of a scalar, you can bring it to the denominator, right. Typically if it is the inverse of a matrix as it usually is, you can't bring things in the denominator, there is nothing like division by a matrix, right. You can only compute the inverse of a matrix, but because this is now a scalar you can bring it to the denominator, in which case this expression for the optimal parameters beta hat becomes sum I going from 1 to n xi yi divided by sum I going from 1 to n xi squared, and this is exactly what we had got here, right. So it is good that the equation we have now manually derived by working through the minimization of the loss function versus a more systematic evaluation through the use of matrices and vectors, they both lead to the same answer, right. So I hope this makes sense to you. We will now consider another example, right. So far we have been dealing with linear regression, right, and simple models, but eventually we will make transitions to non-linear models. As a simple example of a non-linear model, we could consider something like a polynomial, right, and you know that a polynomial also includes a linear function, but it also includes quadratic, cubic and biquadratic functions and so on. So the next example that I will consider will be for a quadratic relationship, right. So let us take the second example for today, which is the application of the L2 loss for quadratic regression in one variable. Okay. So we are going to consider that y, right, the prediction, right, y as a function of x is beta naught plus beta 1 x plus beta 2 x squared, and our objective is to use the L2 loss function to find the optimal parameters beta naught, beta 1 and beta 2, right. So again this is fairly straightforward. We can write the mean squared error loss function, that is 1 over n sum I going from 1 to n yi hat the predicted value minus the true value whole squared. So this is 1 over n sum I going from 1 to n yi minus beta naught minus beta 1 x xi minus beta 2 xi whole squared. Xi squared whole squared, right. So this is the expression that we have, and we will have to take the derivative of this mean squared error with respect to each of the parameters now, right. So in the previous model there is only one parameter beta naught, however in this case we have three parameters beta naught, beta 1 and beta 2. So we will have to take the derivative of the loss function versus each of these parameters, right. And going on later in a few lectures we will be discussing the gradient descent method, wherein this will be formulated in vector form. How do we minimize, right, the loss function versus each of the parameters. So let us go ahead and do this analytically right now. So we want to take the MSE and set the derivative versus beta naught equal to 0, right. So what is this derivative? Like we did the last time, you are going to have 1 over n pop out of the summation will also come out, and then you have the derivative of this whole term here, right. So the term I am talking about is this whole term, okay. So the derivative of that with respect to beta naught is, by the application of the chain rule, twice of yi minus beta naught minus beta 1 xi minus beta 2 xi squared times the derivative of whatever is inside the parenthesis versus beta naught, and that is basically just 1, right. So I hope this makes sense, and then if you set this to 0, this 1 over n will disappear, and this 2 will also disappear. So what you will get instead are 4 terms in the summation, right. So splitting the summation, you have some I going from 1 to n yi minus some I going from 1 to n beta naught minus some I going from 1 to n beta 1 xi minus some I going from 1 to n beta 2 xi squared. And this 1 also I have omitted because ultimately everything is equal to 0, so the minus 1 does not make any difference. So this is a nice expression, right. You see that all the 3 parameters are involved here, beta naught, beta 1 and beta 2, and I am going to take the terms involving the model parameters to one side of the equation. So that becomes beta naught times n, because each term of this particular summation is beta naught, so you are going to just get beta naught, and in the other terms you can take beta 1 out, some I going from 1 to n xi, that is this term here, and the third term becomes plus beta 2 some I going from 1 to n xi squared, right. So these all have been taken to the right hand side. I have moved all these 3 terms to the right hand side here, so the left hand side remains, and that is some I going from 1 to n yi, okay. So we have obtained one equation for these 3 parameters put together, and when we set del MSE del beta 1 and beta 2 to 0, you will get 2 more equations. So let us see how those equations look like. So the second term that we will set to 0 is del MSE del beta 1, and this will be 1 over n some I going from 1 to n 2 times by chain rule yi minus beta naught minus beta 1 xi minus beta 2 xi squared times the derivative of whatever is inside the parenthesis with respect to beta 1, and that is minus xi, okay. So this has to be set equal to 0. So let us do that now. So again what will happen is this 1 over n will disappear, the 2 will disappear, the minus can also disappear. So you would have some I going from 1 to n xi yi minus xi beta naught minus xi squared beta 1 minus xi cubed beta 2, that will be equal to 0. And again you can move all the terms involving the parameters to one side, so that you will have beta naught times some I going from 1 to n xi plus beta 1 times some I going from 1 to n xi squared plus beta 2 some I going from 1 to n xi cubed. This is equal to whatever remains, that is some I going from 1 to n xi yi, right. So this is the second equation that we have obtained, and we can proceed forward to obtain the third equation, right, which will be basically setting del MSE del beta 2 equal to 0. So if you now compute this derivative, that will be 1 over n some I going from 1 to n. Again we will apply the chain rule, so that becomes twice of yi minus beta naught minus beta 1 xi minus beta 2 xi squared times the derivative of whatever is inside the parenthesis versus b2 versus beta 2, and that will come from here, right. The other terms here do not depend on beta 2. So if you take the derivative of these three terms with respect to beta 2, you will get 0. The only term that will contribute is this term that I have marked with an arrow, and that will be minus xi squared, right. And this whole thing we will set to 0, wherein again this 1 over n, the 2 and the minus can be taken to the other side, and what will remain is a simple another simple linear equation for the parameters. So you will have beta naught times some I going from 1 to n xi squared plus beta 1 some I going from 1 to n xi cubed plus beta 2 some I going from 1 to n xi cubed, that will be simply equal to some I going from 1 to n xi squared yi. So what we have managed to do here is we have found three different equations, right, each of them involving beta naught, beta 1 and beta 2, right. They are these equations. Let me number them. This is equation number 1, which involves beta naught, beta 1 and beta 2. Then we have the second equation, which came from the minimization of the MSE versus beta 1, and the third is basically the minimization of MSE with respect to beta 2, right. So these are the three equations. These equations can now be written in matrix form, right, to sort of consolidate all three of them. So let us see what this looks like. So if you wrote this in matrix form, right, in the first equation the coefficient of beta naught is n, the coefficient of beta 1 is some I going from 1 to n xi, and the coefficient of beta 2 is some I going from 1 to n xi squared, right. So that is the matrix, and if you multiplied this by the vector beta naught, beta 1, beta 2, you know that you will get another vector. The first entry of this vector, right, will be the right hand side of the first equation, that is simply some I going from 1 to n yi. Now for the second equation, right, the coefficients of beta naught, beta 1 and beta 2, they are some I going from 1 to n xi, some I going from 1 to n xi squared, and some I going from 1 to n xi cubed, and the right hand side is some I going from 1 to n xi yi. So all these terms can be written inside the matrix. So this is some I going from 1 to n xi, some I going from 1 to n xi squared, and some I going from 1 to n xi cubed. And the right hand side, as we just discussed, is some I going from 1 to n xi yi. And finally, the third row, the third equation is some I going from 1 to n xi squared, that is this term here. Then the second term is some I going from 1 to n xi cubed, that is this entry here, and the third entry is minus some I going from 1 to n xi cubed, which is this term here, and the right hand side is equal to some I going from 1 to n xi squared yi. So this now is a system of linear equations for beta naught, beta 1 and beta 2, and it can be solved to obtain the optimal set of parameters. Beta naught hat, beta 1 hat and beta 2 hat, right. And because these are the optimal parameters, you can put hats inside this equation as well, right. Now the approach that we have shown here is completely general, right. You can easily extend the proposed approach. So the proposed approach can be readily extended to more number of features and more complex models. And the fact that we had to use chain rule, right, repeatedly when evaluating the derivatives, that is also very common in neural networks, right, and it has its own special name. It is called back propagation. So the derivatives are back propagated when you are trying to find the optimal values of the parameters. The other important thing to note is that typically the optimization of the parameters is done numerically. And the most common algorithm used in machine learning is called stochastic gradient descent. Or its variants. And this is something that we will take up in one of the future lectures. Okay, so that brings me to the end of this particular lecture in the course, and today we discussed the application of the mean squared error or the L2 loss function to some example problems, which included a quadratic regression model and a linear regression model. the quadratic regression model had 3 parameters and the linear regression model had 1 parameter because we considered the intercept to not exist, but we were able to show that analytical solutions and very nice expressions are possible. However, mostly because ML models are so complex, we will resort to numerical techniques, but hopefully the exercise done today gives you some insight into what really happens, what may be really happening behind in a computer when you are trying to find these optimal parameters. In the next class, we will continue our discussion on loss functions and take other types of loss functions, so that we have a vast toolkit of loss functions to choose from when we are training the ML model. Usually, right, it may be possible that your ML model does not give good results with a certain loss function, and you may have to try other loss functions, which depends really on the type of noise that exists in your data set. Thank you, and I look forward to seeing you in the next lecture.